Dear students, so last class we discussed different concept of analysis, that is stress concept, strength concept, and load balancing concept. Okay. So in this class we will discuss the based on the location of the prestressing force under the tendon. Okay, how the stress will vary. Okay, and location and shape of the cable. So depends on this parameters, the stresses in top fiber as well as bottom fiber will vary. So how to find out? Using the concepts as we seen in last class. Okay, so first, member subjected to axial prestressing force. So here axial prestressing force is nothing but the prestressing force is applied exactly at the centroidal axis. That means a concentric prestressing force. Okay, so due to this prestressing force, you can see in this diagram. So this prestressing force exactly acting at the centroid. So eccentricity is 0. Okay, under this situation, this is the stress distribution diagram. That is P by A is the direct stress, and due to the external load, the moment will be developed. Okay, that is mg by zt. Okay, so gravity load. Okay, so if external other external loads, that means live load also acting, means it will come mq divided by zt. So this is the final prestressing force, sorry, final stresses produced due to the prestressing force at top and bottom. This is the stress distribution diagram. So next coming to member subjected to eccentric prestressing force. So this is concentric. Okay, so this diagram shows the concentric. Concentric means the prestressing force acting exactly at the center of the beam. Eccentrically means eccentric prestressing point means there will be some distance. The prestressing force applies acting at some distance from the centroid. Okay, so you can see in this diagram. So the same diagram we already seen in the stress concept. So same formula. So stress due to applied prestressing force, that is direct stress P by A, and PE divided by ZT. This is due to the prestressing force. Initially tension goes upward, so minus compression goes bottom, and mg plus mg divided by zt at bottom minus mg divided by zb. This is due to the gravity load, that means sulfite of the beam, dead load moment. Next, external live load moment, mq divided by zt and mg by mq by zb. So this is the final stress distribution diagram. So always in prestressing, member is subjected to pure compression only, so plus value. Okay, so these are all the things I written in the formula wise. This formula we already discussed in the stress concept. So next we will see the first problem. So a rectangular beam of size 250 mm into 500 mm is used to over an effective span of 6 meter. It supports a live load of 10 kilonewton per meter. Okay, so a straight tendon is provided at an eccentricity 80 mm below the centroid of the section. Find the minimum prestress required for no tension under live load at midspan. Compute the stress under sulfite only at midspan and at ends of the member. Okay, first to understand the question. So what are the things they given? They given the member size and effective span. Span is given 6 meter and live load is also given. Okay, so a prestressing force applied at an eccentricity of 80 mm below the centroid of the section. So find the minimum prestress required for no tension. So under no tension condition, what is the prestressing force? And we have to find stresses also under sulfite only. So don't include a live load. Under sulfite, what is the stress distribution at midspan and at support. So now first write the basic parameter, that is area and Z value. So area 250 into 500 is the size, and Z value for rectangular section BD squared by 6. So B is 250 and D is 500 squared by 6. So 10.42 into 10 power 6 mm power cube. Next, loading at midspan. So at midspan, what is the sulfite? 0.25 into 0.5 into 1 into 24. So 24 is the density of the concrete, equal to 3 kN per meter. So dead load moment. What is the dead load moment? What is the dead load given? We already found it is 3 kN per meter. So since it's UDL load, it is like acting UDL load. So WL squared by 8. This is the maximum bending moment formula. And the live load, it is given in the question. It is 10 kN per meter. So that it is 10 into 6 squared by 8, WL squared by 8, it is 45. So dead load moment is 13.5 kilonewton meter, and live load is 45 kilonewton meter. Okay. So next, so this is the diagram, and shown the eccentricity also, eccentricity of the cable. Okay. So next, stress condition. So write the formula, P by A plus PE divided by ZB. This is the bottom stress formula. So substitute all the parameters. So we don't know the eccentricity. We don't know the eccentricity. In first question, they asked only eccentricity. So except eccentricity, all the parameters we know. Moment we know, area, Z value, everything we know. So substitute all the values under no tension condition. So please be remember, under no tension condition means this equation will be equal to 0. Stress is 0. That is the no tension condition. So finally we got the precessing force, 358.1 kilonewton is the precessing force required. Okay. Next, stress due to sulfite only. So here, stress due to sulfite, we have to find at bottom as well as top. First at midspan. Okay, at midspan, so the formula is P by A plus PE divided by ZB minus mg divided by ZB. So this is formula for at bottom, inferior. Okay, so F inferior means stress at inferior means at bottom, superior means at top. So substitute all the values. P we know 358.1 and the eccentricity 80 mm, mg 13.5 into 10 power 6. You convert all the values in terms of Newton mm. Okay. So same like F superior, that means at the top, substitute all the values, finally you can easily get the answer. So at midspan, the bottom stress is 4.31, at top it is 1.41 Newton per mm square. Next, at support. So if at support means at the edge, okay, so the moment value will not come. Okay, so maximum moment where it is occurs at midspan. So that we used at midspan, we used mg divided by ZP. But at support, the moment value is 0 because it is a simply supported. So at simply supported end, in case of simply supported beam, at end of the support end, the bending moment value is 0. We already know. So this term, okay, you can see this term will get 0. This term will get 0. So this term will not come. So accept this mg divided by ZB, write the term and find out the stress. Okay. So you can see here, if you include at midspan, it is 4.31, but at support, it is excess. That means 5.61. Okay. So at the top, at midspan, it is 1.41, but in case of at support, it is less, 0.11 Newton per mm square. Okay. So this is the stress distribution diagram. Okay. So I hope all of you understand the first problem. So please read the question very carefully. If no tension occurs under that condition, if they ask to find out P means, you have to equate the formula is equate to 0. And at midspan, we have to consider both mg and as well as mq. In case of live load also consider. If in this problem they asked to consider only sulfide. Sulfide means only dead load. So we consider only mg. mq not considered. So in at support, this mg also will not come because simply support at the end, the moment value is 0. Okay. So next come to example 2. Okay, I'll read the question. Please follow. A rectangular concrete beam 250 mm wide and 300 mm deep, spanning over 8 meters, is prestressed by a straight cable carrying an effective prestressing force 300 kilonewton. So here prestressing force is given. Located at an eccentricity 60 mm. So eccentricity also given. The beam supports an imposed load. So UDL load is 2 kilonewton per meter. This is called live load. Okay. Calculate the resultant stress distribution for the central cross section of the beam. The density of the concrete is 24 kilonewton per meter cube. Okay. Find the magnitude of the prestressing force with an eccentricity of 50 mm, which can balance the stress due to dead load and live loads at the bottom fiber of the central section. Okay. So first read the first question. What they are asking, calculate the resultant stress distribution. Okay. First we will see that one. So beam properties, calculate the area 250 into 300 and section modulus BD square by 6. These are all common for every problem. So next, self height of the beam. Okay. Self height per meter. So next, dead load moment. Dead load moment is WL square by 8 and live load moment also WL square by 8. So calculate the self height first. It is 1.8 kilonewton per meter. Okay. So area they calculated in terms of mm square. So convert mm square into meter square. For that, divided by 10 power 6 and multiply by 24. Okay. Next, dead load moment, it is 14.4. WL square by 8, it is 14.4. And the live load moment, it is 16 kilonewton per meter. So live load given in the question. Okay. So in the first question, calculate the resultant stress distribution on the central section of the central cross section of the beam. Okay. So you can see here, stress at the top. Stress at the top. So here at stress at the top, we consider P by A minus PE divided by ZT plus mg divided by ZT. Okay. So here also we are considering only dead load moment. So we are not considering live load moment. So because the resultant stress distribution of the central cross section of the beam, the density of the concrete is 24 kilonewton per meter cube. Okay. So here they given only density of the concrete. Based on that, we have to consider only dead load. So if sometimes in the question, if they consider both, means you have to consider both dead load and live load. Okay. So next, stress at top, it is substitute all the values P by A minus PE divided by ZT plus mg divided by ZT. So we got 3.04 Newton per mm square. Stress at bottom, so P by A plus PE divided by ZB minus, actually this is not Q, this is mg divided by ZB. So mg value only 14.4. You can see here they substitute at 14.4. So at bottom it is 4.96. Okay. So next, prestressing force. So how to calculate prestressing force using this formula? Okay. So the P by A plus PE divided by ZB minus mg divided by ZB minus mq divided by ZB equal to 0. So using this formula, you calculate the prestressing force. Okay. So you can see the second question. Find the magnitude of the prestressing force with an eccentricity 50 mm. So here you can ask one question. Sir, already prestressing force is given 300 kilonewton. Why again they are asking prestressing force? So this 300 kilonewton prestressing force for 60 mm eccentricity. Okay. So understand that one. So this 300 kilonewton is for 60 mm eccentricity. So but here they given consider eccentricity is 50 mm. So now eccentricity is reducing. Under this 50 mm, what is the prestressing force? Okay. So for that, we used the equation, same equation. Okay, P by A plus PE divided by ZB minus mg divided by ZB and minus mq divided by ZB equal to 0. That minus term will go this side, means you can get this equation. Okay, so that on simplifying, you got P value is 304 kilonewton. So students, from this problem you can understand, if precessing force, the applied precessing force eccentricity reduces. So initially it is 60 mm, the precessing force is 300 kilonewton. If precessing force eccentricity reduces 60 mm to 50 mm, the applied precessing force got increased. So from this problem, we can understand the concept. Okay, you precess, the eccentricity reduces, precessing force increases. Okay, students. Okay. So next, this is the T-beam problem. So I'll read the question. A precessed concrete T-beam having a cross section of flange 1200 mm wide and 200 mm thick rib is 240 mm wide and 1000 mm deep. The beam carries a load of 12 kN per meter over a span of 16 meters. Determine the precessing force and its eccentricity to produce net stress equal to 0 and 12 megapascal at top and bottom fiber. This is the very simple problem. Okay, previously, what is the difference between previous problem and in this problem means? So previous problem, they given only rectangular section. But in this problem, they given T-beam section. That is the difference. So you can see here, this is the cross section of the beam. So flange thickness, flange size is 1200 into 200, and web rib all are same. Okay, web size is 1000 mm into 240 mm. Okay, so there will be a UDL load is acting. It is 12 kilonewton per meter. The length of the beam is 16 meter. So the beam properties is, so first calculate the area of the section. So since it is the unsymmetrical section in x-axis, in y-axis it is symmetrical, but x-axis it is unsymmetrical. So we need to calculate z value. So what is the z formula? I by y. So for calculation of moment of inertia and yt and yb, we need to calculate the centroid. So calculate the centroid. For the unsymmetrical section, how to calculate the centroid? So first 1000 into 240, you can see here. So either you can take the centroid from top as or at bottom. So I am taking centroid from bottom. So you can see here, first calculate the area into h. That means 1000 into 240 into, what is the centroid of the first cross section? This is first element, this is second element. Okay, so 1000 divided by 2, it is 500. Okay, so next plus 1200 into 200 is the cross section area of the flange. So what is the centroid distance? So from here to bottom. Okay, so what is the centroid distance? 1000 plus this 200 divided by 2. Okay, so we have to take from here to here. So already this is 1000, this distance, centroid distance is 100. So 1100 divided by area of this two element. Okay, this is element 1 and this is element 2. I hope already you know how to calculate for unsymmetrical section, centroid and moment of inertia. So from bottom, the centroid height is 800 mm. So how to calculate moment of inertia? So for that moment of inertia, I split it into 2. You can see here, I am taking, this is the first element up to this, and this is the second element. So 1200 into 400 mm is the height. Okay, so you can see here. So Ix is equal to 1200 into 400 cube by 12. So first I am considering this is the rectangular section. So for rectangular section, it is BD cube by 12. So next we have to minus this shaded area. So that shaded area What is the size? It is 960 into 200 cube divided by. So students, here you can see here BD cube divided by 12. So instead of 12, they actually printing mistake. It is not 3. So these are all 12. Okay, BD cube by 12. Okay, the rectangular section moment of inertia we already know BD cube by 12. So substitute that formula. So I can get first we have to consider the whole thing. We have to consider the whole thing. And after that, we have to minus the shaded portion. Okay, so this is the minus the shaded portion. Plus at the rib, it height from the centroid, the height is 800 mm and the breadth 240 mm. So this is the corresponding 240 into 800 cube divided by 12. So we got 6.4 into 10 power 10 mm power 4. So from this ZT is equal to Ixx divided by Yt and Zb is equal to Ixx divided by Yb. So substitute Ixx value and the corresponding centroid of bottom and centroid at the top. Okay, you can get the ZT and Zb value. So here onwards, so same procedure as per previous problem. So sulfite per meter. So calculate the sulfite of the beam. Okay, how to calculate sulfite? So we know you can see here. So calculate the area. We know the area. So area into 1, we get the volume into 24. Next, dead load bending moment. So all are given in mm square. You convert it into meter square. Next, dead load moment. It is WL square by 8. That also we calculated 1.52 into 16 square by 8. And live load moment, the external load is 12 kilonewton per meter is acting. So 12 into 16 square by 8. So next, stress. Calculate the stress at top and bottom. So P by A minus PE divided by ZT plus mg divided by ZT plus mq divided by ZT. So substitute all the values except P and PE. Okay. So because what they are asking, determine the, you can see the question, determine the prestressing force and its eccentricity. So these two values we don't know. Okay, here two unknowns is there. Except this P and E, all the values are known values. So substitute all the values in this equation, the stress at the top equation. Finally, you got one equation in terms of P and P. You keep it with this. It is equation number 3.1. So at bottom, same the formula P by A plus PE divided by ZB minus mg divided by ZB plus minus mq divided by ZB is equal to 12. So why it is 0, it is 12? It is given in the question. Okay, stress at top is 0, stress at bottom is 0. Under this condition, what is the precessing force? You can see here in the question. So determine the precessing force and its eccentricity to produce net stress equal to 0 and 12 MPa at the top and bottom fiber. Okay. So for this, we have to find. Okay. So at top means it is 0. We have to equate into 0 and bottom we have to equate into 12. So under this condition, there will be one more equation will come in terms of P and E. So solving this equation, that means this equation and this equation. So in this two equation, this P and E are the unknown values. You can solve using calculator or manually. You can get P value first. After that, substitute any one of the equation with the P value. You can easily get E value. Okay. So this problem is very much important, student. Same this problem. Like this problem only they will ask in the question in this topic. Okay, under Flexure. Okay, so if any I section or unsymmetrical I section or unsymmetrical T section is a section like that they will give, means this is a section they won't give, either I section or T section they will give. First to calculate the basic parameters, area, and calculate the centroid distance. From the centroid distance, calculate the moment of inertia Then calculate ZT and ZB. Then self-weight of the beam, dead load moment, live load moment. These are all the common thing. Then apply the formula, stress condition formula, top and bottom, based on the stress value, and find out P and E. That's all. So I hope all of you understand these problems. So similar problem we will see in the next class.